Hello, welcome back. In this exercise, we're going to determine the differentiability of a function. And this function is given as a piecewise function. And the point where we're looking for the differentiability is x equals 1. As you see on the left of x equals 1, the function is taken to be x minus 1 cubed. On the right of x equals 1, the function is x minus 1 quantity squared. In each side of the equation, the function description is different. Let me just remind you an alternate form of the derivative at a point. So normally we used to use the limit definition where delta x was going to 0, and we were looking at the ratio of f of x plus delta x minus f of x divided by delta x. But alternatively, you can use this limit expression as the derivative of the function. By the way, and here the case is that since on the left and on the right the function description is different, we're going to look at this limit from the left and from the right, and if both limits are equal, then we're going to say that this limit exists. All right, we have two different limits to check. One is the one that we approach one from the right, so the function is x minus 1 quantity squared. And by the way, f of 1 is equal to 0 because c equals 1 for this problem. And for the left limit, we're taking the function x minus 1 cubed, and the function value is still the same, 0, and divided by x minus 1. At this moment, if you just plug in 1 for x, then you're not going to get anything because everything is going to reduce down to 0 over 0, which is an indeterminate form, and the same thing here. So what we can do is just we can simplify the top and the bottom if we can. And in fact, since the top is x minus 1 quantity squared and the bottom is x minus 1, so I can write this limit as just x minus 1 after dividing top and the bottom by x minus 1. The limit is the function evaluation, so it turns out to be that the right limit is 0. And for the left limit, we're going to essentially apply the same type of algebra. So x minus 1 is a common factor at the top and the bottom. Dividing top and the bottom out by x minus 1 yields x minus 1 quantity squared. And at this moment, the limit is the function evaluation. So plugging in 1 for x, we get 0. So since the left limit and the right limit are equal, the function is differentiable at point x equals 1 because this limit of this function exists. And that's in fact f prime at 1. So in other words, f is differentiable at point 1. F is differentiable now everywhere because if x is not equal to 1, the top piece is differentiable, the bottom piece is differentiable, and since f is also differentiable at x equals 1, the conclusion here is that the function f is differentiable for every x. And here is a graphical outlook of the function. This blue curve has a horizontal tangent line at point x equals 1, and you can easily calculate the derivative of each piece if you're in the left of 1 or right of 1 by using the limit definition. All right, thanks for watching. I'll see you in another video. Bye.